Hey guys, Mr. Betts here. I want to talk about a way that we can use derivatives to get a little more information about functions that we may not have a whole lot of information about. In particular, I want to talk about a method that we can use straight lines to approximate values of a function that's a curve, and in particular, curves that we don't know the values of at certain points. So this is going to be particularly useful for things like trig functions, where we know the sine of 0, we know the sine of pi over 2, we don't know the sine of 0.1, we don't know the sine of 12. But we can use values of sine that we do know and use them to approximate values that we don't know that are close to them. So let's just get a little background here. We know that if a function is differentiable at a point, it's also continuous. However, we also know some other information if a function is differentiable. So this is one of the two definitions of the derivative that we've talked about. And it just takes this difference quotient here, f of x minus f of c over x minus c, which is the slope of the line through these 2 points. That's a c. And what it does is it looks at what happens as when we hold c constant, because we're looking for the derivative at that point, and this point approaches that point along the curve. And we look at the slopes that we get between those 2 points as they approach each other. And if those slopes approach a particular value, then we say that derivative exists, and that's the slope of the tangent line. So we're finding slopes of secant lines, and if the slopes of the secant lines approach a particular value, that's the slope of the tangent line. What that means is if we look at, say, this is x equals c right here, and this is x, and it's approaching here, what we're getting are a bunch of values for this limit that are approaching some particular slope. So graphically, what that's going to look like is this. So this is f of x equals e to the x, and this is the tangent line at x equals 1, or I'm sorry, x equals 0. And so this is what we get with that limiting process. We get the slope of this line, and then in conjunction with the value of the function at that point, we can actually write the equation of that line, which in this particular case is y equals x plus 1. So if we look at what happens, though, as we get really close to here, we get a property for this curve that's called local linearity. And I want to be clear, this is an informal way of thinking about what a curve looks like. But the idea is in this neighborhood around a point of tangency, so close to that point of tangency, the curve is going to look a lot like a straight line. So it's not real obvious if we look at the picture like this, but if we take just a little portion of it and we zoom in, the curve and the line are almost indistinguishable. So by looking at a really small portion of it, the curve looks a lot like a line. And that's because of the value of that limit approaching a particular slope. That means that if we're picking values on the function and the point of tangency, that slope is approaching the slope of this line right here. So this idea of local linearity is going to happen anytime the derivative exists. So in other words, a function that is a curve is going to behave like a line in a small enough neighborhood. So using that idea, we can take advantage of it to figure out values, or at least approximate values of the curve near the point of tangency. So the way we're going to do that is we're actually going to write the equation of the tangent line. Remember, to get the equation of the tangent line, we need both a point, which I'm going to call c comma f of c, and we need a slope, which the slope is going to be f prime of c. And using those two things, we can write the equation of the tangent line. So in this case, it's going to be y minus f of c equals the slope, which is f prime of c, times x minus c. So that's point slope form. If you want to get y by itself, you can write it as y equals f of c plus the derivative times x minus c. And this equation right here is actually a formula for a linear approximation. So that's the equation of the tangent line. But if we find the values of this around C, so if we plug values of x in close to C, we're going to get values on the line that are going to be really close to values on the function. So for example, in this particular example, when we're looking at the e to the x function, if I want to know what, say, e to the 0.1 is, which I'm going to do in another example, if I plug it into the equation of this line, which is y equals x plus 1, that means that e to the 0.1 is going to be about 1.1. And it turns out that's actually really close. So what we're looking at here is the difference between the value of the function on the blue line and the value, the value of the function on the red dotted line and the value of the line itself on the blue, and they're going to be really close to each other. Now, I do want to point out that the further away from our point of tangency we get, the bigger this gap is. So the approximation is obviously going to be better the closer to the point of tangency, because this gap here, the vertical distance between the line and the curve, is telling us how far off we're going to be. So some things to keep in mind. If the point of tangency is at x equals c, then when we're approximating the value of the function close to c, we can also tell if the approximation is going to be too big or an over approximation or too small. So remember concavity, we've talked about before, and concavity just tells us which way a curve is curving. So concave up is going to look more like a U, and concave down is going to look like an upside down U. So if a curve is concave up, like this e to the x curve is here, then when we graph the tangent line is going to be below. So if a curve is concave up, then our approximation from the tangent line is going to be too small, or an under approximation. On the other hand, if a curve is concave down, then our tangent line is going to be above the curve, and so a concave down function is going to have linear approximations that are too big. So knowing if a function is concave up or concave down can tell us if our approximations are too big or too small. So this is a really important idea, and later on we're going to use calculus to actually compute concavity. But for now, I'm going to count on you to know the shapes of some basic functions like e to the x, which we see here is concave up. Y equals x squared is going to be a concave up function. The sine function is concave up in parts and concave down in parts. So we can see from 0 to pi, the sine function is concave down. From, say, negative pi to 0, it's concave up. So for values to the right of 0, our straight line is going to be too big, or an over approximation. For values of sine to the left of 0, our straight line is below the curve, because the curve is concave up and the approximations are going to be too small.